Okay, so welcome back to the segmentation section series, and we were discussing about segmented paging. But in this video, we'll start with some questions, and then we'll proceed for the explanation of the segmentation paging. How does this happens? So let's say we have before starting, we need to understand that in segmentation we were doing what? We were dividing the segment into equal size pages. Okay, so we were dividing these segments of the LAS, okay, of the LAS into equal size pages. So each segment into equal size pages, and then we were applying paging onto that, and then paging is applied. Okay, so each segment is divided into equal size pages. Please note, each segment divided into equal size pages. Equal sized pages, and further paging is being applied on that pages. For the pages, paging is applied for each segment, because we are doing this because the segment size is very huge, so we are not bringing the entire segment into the main memory. We are bringing the pages of the segment into the main memory, and hence we can say that page size, okay, the page size of each page of the segment, right, page size of each segment is same as the frame size of PAS. So we'll see, make a look into this. So please make a note of this, and let's see in a question what I'm trying to say. That if we have a system of that introduces segmented paging architecture, and segment divided into 1K pages. Okay, so each segment, this means each segment is divided into 1K pages. So definitely paging is applied onto segment, right? So if the segment size is D, then it will get divided into two components. So first is P1 and second is D1. So P1 becomes how many? 1K pages for each segment. So 2 raised to the power 10, that is P1 is allocated 10 bits, right? So this is clear from this. Now, each page size is having 512 entries. Now we are given 2K pages, and each page having 512 entries. So 512 means 2 raised to the power 9. So page offset is 9 bits. So from here we get D equal to 19 bits. So what is D? D is nothing but the number of bits required to represent a segment. So for this D, it got divided into certain pages, and each page is having uh, 512 entries. So this becomes 19. So D is nothing but 19 bits. From here we get this. Now segment number, that is S, requires 15 bit to represent all the segment to represent all the segments of LAS. That means definitely S will become 15. So from here we can get S equal to 15 and D equal to 19. Hence LA becomes S plus D, that is equal to 34 bits, right? So we got the LA. That is the logical address. Now let's say what is being asked here. And yeah, one more thing, that frame number requires 18 bit to represent all the frames of PAS. Frame number requires 18 bits to represent all the frames. So this 18 bit is nothing but frame bits, that is f equal to 18. And now the question comes that physical address is what, right? So if we say physical address, it constitutes of this frame bits and d is the what size of each page of the segment, because here we are not bringing the segment, we are bringing the pages of the segment, that is d equal to d1. D is nothing but d1, please note. So d1 is 19 and this is 18, so altogether pa becomes just a second, 18 bit is required to represent all the frames. So d is not 19, d is 9, d1 is 9. Okay, so we are taking d1. So D1 equal to 9 bit. So it is altogether 27 bits. Now why D1 we are taking 9? I mean this D is 9. So this I'm just going to tell you why. Before that, let's say the page size of the segment table is page size equal to number of entries, and number of entries nothing but number of pages into PTE. So number of pages of the segment is 1k, and PTE is nothing but what is the content of the page size. So we have been given PTE as 4 word, so it is 4 kiloword, this is the page size. Now the question comes, why we here take the D as 9? Okay, this is one question that I would like to put light into. So let's see why we are taking this D as 9, and this will clarify the previous lecture doubt that we were facing while segmentation. So let's say we have this logical memory, and we know from user point of view we have thought that entire program is divided into certain segments, right? These are our segments. So let's say here altogether the total number of segments depends upon the uh, number of segments and each segment size, right? So if it is the LAS, so let's say each segment size, let's consider it as a 16 word. Okay, so altogether if not 16 word, if we consider each segment of a particular size, let's say we have divided into, or let's say we have this LAS, and this LAS is equal to let's say 256 kiloword. Okay, the size is 256 kiloword, and we have divided it into 18 2 raised to the power 18 segments, like 256 kilowatt kilo segments, so 0 1 and so on up to 2 raised to the power 18 minus 1. So total number of segments here, from here we can say that total number of segments is nothing but 2 raised to the power 18, right? This I want to illustrate. Now each segment we are not bringing into main memory like previously in segmentation we were doing. We are applying paging onto each segment. Okay, we are not bringing the entire segment into the main memory, we are applying paging into onto each segment, and then we are bringing the pages of this segment into the main memory. That is why D we have taken as D1, not the exact D. So let's say if the CPU generates a logical address consisting of a segment number and the segment offset. So if it is, let's say segment number is, if they are all together 18 to 2 raised to the power 18 segments, so 18 bits are used to represent the segment, and let's say each segment is of size uh, let's consider each segment size is 64 kiloword. Okay, so altogether 16 bit is used to represent the each segment. Now if it generates this, so we have one base table. Now here this table will constitutes of all the segment number and their corresponding page table base address. Okay, so here X and L will be the size of segment. What is the size of each segment, right? And based on that we have this L, and X is nothing, and this is what number of segments. So each segment is mapped to a particular page table, and X will contain the base address of that page table. So first we are just comparing if D is lesser than L. If it is a no, then it is a trap. If it is a yes, then what we are doing, we are taking the X from here. Okay, for the X is correspondent to whatever segment the CPU tries to access. So X is the base address of the page table of that segment. So we are first loading the page table of that particular segment. So this is X base address of what? Base address of page table of segment whatever CPU has accessed. Now here what we are doing, we are dividing the component of D into two parts, like D1 and sorry, it is P1 and D1. So if we are, since we are having this page table of the segment, then there are certain pages into that. So each segment has been divided. This 64 kW has been divided into certain number of pages. Okay, and each page having size 1 kilowatt. So each page size if 1 kilowatt, so the page offset will be something called 10 bits used to represent this, and 0, 1, 2, so on up to 6 bit is used to represent each page. So altogether there will be 6 pages, and each pages with size 10 kilowatt. So this is the page table. Now this is what, this P1 is the page number of segment, and now D1 will be the page size of the segment, and here it will be our frame number. Okay, so here the for each segment, like for each in each page we are having the frame number, so this will give us the frame number, right? And this D1 will be giving what, the offset of the particular instruction that we are trying to access. So this is the D is equal to D1. Why this D is equal to D1 is, you can assume, like if we have this main memory, and in this we have a lot of frame, so this is something called the frame number. Okay, so for each frame, in each frame we are holding each page of particular page, so this corresponds to the page number of the segment, and accordingly we have the frame number for this page number, and it contains the pages of the particular segment that we are trying to access. And here in each page, D corresponds to the word number, so it's this D is nothing but the D1. Okay, so this is how it is related. So please note, this point is very important, right? So I know the figure has become very much dirty, but that is what I want to illustrate. Let's see this in next question also. This will get more clearer. So if we have again a system that introduces a segmented paging architecture, and the segment is divided, when we say the segment is divided, we mean each segment divided into 8K pages. So 8K pages for each segment. So when we are introducing the paging, so number of pages is equal to uh, P1 equal to 13 bits, right? So if D is the segment size, D is the segment size. So this segment has been divided into equal number of pages, equal size pages with P1, and each page size is D1. So 13 bits are allocated to P1. This you need to clarify. Now each page, each page of each segment having 2K entries. Now 2K entries is nothing but 11 bits are used to represent the page offset. So each page having page offset of 11 bits. So D1 becomes 11 bits, right? And the segment number means altogether how many segments are present in the LAS. So segment number requires 19 bits. So definitely this S becomes clearer. So S becomes 19 bits, and it is nothing but S plus D. S is 19 bit and D is 13 plus 11, 24 bits. So altogether we have got the LA here, logical address, that is nothing but 43 bits, right? So LA is clearer from here, right? And then it is saying that memory is byte addressable, okay, and PAS is 512 bits. So PAS means physical address space, and it is 512 KB, and PAS will contain the frame, and each frame is having size equal to the page size. So if we want to calculate the number of frames, so what will be the number of frames? Number of frames equal to 512 KB, and each frame is equal to each page of the segment. So each page is having a size of 2k 2k bits are used to represent each page. So overall size is 2k kilobyte, right? So number of frames becomes um, 256. So number of frames become 256. So F becomes 8, and D1 is definitely, or we can calculate it from here also, and D1 is nothing but page size, that is 11 bit or frame size. So we have a PA is equal to F plus D1, and that is equal to 19 bits, right? So we have PA equal to 19 bits. Okay, if I am not wrong, F is equal to this is 43 bits LA, and this is the PA. So the PA becomes kilobyte, and D1 is 11 bit, and we have F. So F is the number of, okay, sorry, it is number of frames required. So if PAS is 512 kilobyte, so number of frames, we are not dividing it by 2 KB. Number of frame bits will be 19 bits. Why? Because, so this has to be clearer. Number of frames is 19 bits because PAS is 512 kilobyte. I got confused here. So PAS if 512 kilobyte, and memory is byte addressable. Okay. So number of frames is equal to 512K, and that is equal to 2 raised to the power 19. So it is 19 bits, right? This is 19, and each having size of each page having size of D1 11 bits. So this is 11, and then we are adding these two together, so it is 29 bits, right? Now, the next question comes of the page table size of the segmented paging table. So we have been given PTE. So it is 8 bit, that is 1 byte. And then we have the altogether number of pages. So number of pages is nothing but P1, and P1 we already calculated 13 bits. So 2 raised to the power 13, and that is equal to 8 KB. So this is 8 KB. One thing point to note here that whenever we are having the PAS, so PAS in PAS we will be having number of frames, and number of frames is dependent on to not the page size, is dependent on to how we are categorizing the memory, because here this is giving us the number of pages of the segment, which is not equal to the number of frames, right? So this thing we need to clear. This frame bit, that F is being stored with each corresponding to each page. So here this frame bit is giving us the F, and from here we are accessing the particular frame in which this particular page is being kept. So for each frame we are keeping the pages, and this page size, this frame size is equal to this page size. Okay, this one, right? Let's see one more question. I think it is much clearer from this. So but let's illustrate this one in this question also. So LAS is given as a 2 raised to the power 16 byte, and then we have PAS is also given as 2 raised to the power 16 byte. Number of segments in the LAS is given as 8. Okay, so it is 2 raised to the power 3. Now we have been given the segment size. So each segment is equal to and we don't know the number of pages in which we have divided the segment into. So let's say we take that the page size or in which the segment has been divided into is x. Page size is x. If number of segment is 8, so definitely in the LAS S correspond to 3 bit, and D, let's say D is the size of the segment. So let's say we are using X bit to denote the D, so segment size becomes equal to 2 to the power X, right? So this segment size becomes equal to 2 to the power x, and he from here we can calculate d also, right? I mean, just a second. First, forget about this. If it is 2 raised to the power 16 byte and 3 bits are allocated to s, then remaining 13 bits are allocated to d. The segment size becomes 2 raised to the power 13, right? And let's say number of pages we need to calculate. If we take the page size equal to x byte, if it is a byte addressable memory. So if we calculate the total number of pages, so total number of pages becomes segment size divided upon the page size, like this we can calculate, right? So let's say that if right now we have this entire logical memory address. So S and D, so the S is 3 bits and this D is 13 bits, right? Now this D gets divided into P1 and D1. So let's say we are taking P1 as X bit. Okay, so number of pages is 2 to the power X. Let's not take the page size here. Let's take this as bits only. So P1 is X bit and D1 is 13 minus X, right? So number of pages become 2 raised to the power x. Now we are given that PTE, that is page table entry, is 2 byte. So 2 raised to the power x into 2 byte becomes equal to the page size, a page table size, right? So this is equal to page table size, each page table size. Now if we are given that the page table size is equal to the uh, segment page size of the segment. Okay, so page size of the segment is 2 raised to the power 13 minus x. So 2 raised to the power x plus 1 equal to 2 raised to the power 13 minus x, right? So 2 raised to the power x into 2 is equal to 2 raised to the power 13 by 2, right? So it becomes 2 raised to the power x into 2 raised to the power 2 equal to 2 raised to the power 13. That's how we calculate the x. So 2 plus x equal to 4. 2 raised to the power 2 is 4. So it's something called uh, 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 um, let me illustrate it down. So it's something 2 raised to the power x into 2 is equal to 2 raised to the power 13 by 2 raised to the power x, and it's 2 raised to the power x into 2 raised to the power x into 2 equal to 13, 2 raised to the power 13, and then it becomes equal to uh, 2 raised to the power 2x. Okay, and we are just using this to 12. So 2 raised to the power 12. So 2x is equal to 12 and x is equal to 6. That's how we calculate x. And if we have calculated x, we can calculate 13 minus 6, that is 7. So we can calculate the segment size as 2 raised to the power 7. So this is the way we calculate the segment size. So altogether, this was all about segmented paging, and I hope I was able to clarify the doubts in the previous section. So yeah, that's all for this part, and please keep watching and do like, share, and subscribe.